Let's have our next speaker, Barnabas Janzer from Oxford and ETH, telling us some Turán type problem for 0-1 matrices.
Thank you for the invitation. So all of this is joint work with Oliver Janzer van Magnan and Abhishek Methuku. And I'm going to start with some background about the extremal numbers or Turán numbers of graphs. So as we've already seen in the previous talk, x and h is the maximum possible number of edges in an m-vertex graph, which doesn't contain h as a subgraph. So I'm not going to go into too much detail about this because, for example, we've already seen this. But I'm going to mention that the Erdős-Stone-Szymonovich theorem determines this as the asymptotic value of x and h when in terms of the chromatic number of h. However, it only gives the asymptotic behavior when the chromatic number is at least 3. Because if the chromatic number is 2, in other words, when the graph is bipartite, it only tells us that the extremal number is little o n squared. So it doesn't tell us the actual behavior of this function. And because of this, it's still a major open problem in the area of extremal graph theory to determine the behavior of the Turán number of bipartite graphs H. So what is known about the Turán numbers of bipartite graphs H? Even some very specific cases are unknown, like very natural specific cases. For example, the Turán numbers of even cycles or complete bipartite graphs are not known in general. We have some upper bounds, but we have no matching constructions. And one of the few general theorems that are known to be tight is this result of Füredi from 1991. And I'm going to mention this result specifically because it's going to be relevant to our talk. So it says that if you have a bipartite graph such that every vertex on one side of the bipartition has degree at most t, then we can upper bound the extremal number of the graph as some constant times n to the 2 minus 1 over t. For example, if you have a 4 cycle, then every vertex on the one side of the bipartition, in fact, every vertex has degree at most 2. So this gives us an upper bound of n to the 3 halves, which is known to be tight for the 4 cycle. And in general, we have this n to the 2 minus 1 over t formula, which is again known to be tight for general t. For example, if h is complete bipartite KTR, where R is large enough. It's not quite known to be tight if it's KTT for general T, but at least it's tight for KTR if R is large. So this theorem was originally proved by Füredi in 1991, and it was later reproved by Alon, Krivelevich, and Sudakov in 2003 using the dependent random choice method. So nowadays, I believe this is usually proved using dependent random choice. Okay, so this is the extremal number of graphs, and I'm going to move on to the main topic of this talk, which is the extremal numbers of matrices, of 0-1 matrices. And I'm going to define the analogous notions for matrices that we had for graphs. I'm going to say that if you have a 0-1 matrix M that contains another 0-1 matrix A, if you can find basically the pattern of A in M, by which I mean that you can delete possibly some of the rows of M and also some of the columns of M. And you are also allowed to turn 1 entries into 0 entries such that you're left with A. So let's have a look at this example. If M is the matrix on the left, it will contain the matrix on the right because we can just delete the last row and turn 2 of the 1 entries into 0 entries, and then we're left with the pattern on the right. So it's important to note that just like in the graph case, we didn't insist that our subgraph is an induced subgraph. Here as well, the analogous thing is that we don't insist that the matrix is induced. In other words, we are allowed to turn 1 entries into 0 entries after deleting the rows or columns. And just like for graphs, I'm going to define the extremal number of the matrix. I'm going to denote it with a capital E, the X here, just to make it clear that we're talking about the extremal numbers of matrices and not the extremal numbers of graphs. So the extremal number of the matrix A is the maximum possible number of one entries in an n by n 0, 1 matrix which doesn't contain A. So what is the relationship between the extremal numbers of graphs and the extremal numbers of matrices? Actually, there's a direct connection between the two. Because if you have a 0, 1 matrix A, that naturally corresponds to a bipartite graph. It's basically the adjacency matrix or the bi-adjacency matrix of a bipartite graph. So more explicitly, you can take a graph, a bipartite graph, which has on one side of the bipartition vertices corresponding to the rows of the matrix, and on the other side of the bipartition columns, vertices corresponding to columns of the matrix. And you join a row vertex to a column vertex if the corresponding entry in the matrix is 1. So this way, for each matrix A, we define a corresponding bipartite graph, which I'm going to denote by HA. And for example, if you have this 0, 1 matrix shown here, then that can easily be checked to be correspond to a 6 cycle. So it's important to note that for every matrix, there is up to isomorphism a unique graph which corresponds to it this way. But the converse is not true. So if you have a bipartite graph that corresponds to several matrices, because you can order the vertices in many different ways, and each of those orderings will give a different adjacency, bi-adjacency matrix. So in some sense, the extremal theory for matrices corresponds to the ordered Turán problems. The Turán problem where we additionally assume that there is an ordering of the vertices of our bipartite graph. So because of this connection between 0, 1 matrices and bipartite graphs, it's not difficult to show that the extremal number of a matrix is at least as big as the extremal number of the corresponding bipartite graph. So if you can avoid the bipartite graph, then you can definitely avoid the matrix as well, using this correspondence for both the small matrix and the large matrix, which has to avoid A. But although it was initially conjectured that these are usually roughly the same order of magnitude, these two extremal numbers, this is actually not true, and the extremal number of the matrix can be much larger than the extremal number of the corresponding bipartite graph. And this was proved by Pach and Tardos in 2006, who showed that you can have examples of matrices which correspond to arbitrarily long cycles, yet their extremal number is at least n to the 4/3. So we know that the extremal number of cycles has extremal, if you have a 2k cycle, then its extremal number is at most some constant at n to the 1 plus 1 over k. So the exponent tends to 1 as k tends to infinity. However, this example shows that you can have for the matrix exponent being not dropping below 4/3. So to summarize, the extremal number of the matrix is low bounded by the extremal number of the corresponding bipartite graph, but it can be much bigger than that. So I'm going to say a few words about the history and the motivation for these problems for studying the extremal numbers of matrices. So there's this old question of Erdős and Moser, which asks for the maximum possible number of unit distances among the vertices of a convex angle. And Füredi was working on this problem. So the best known lower bound for this is linear, but the best known upper bound was very far away from linear. And Füredi was working on this problem and managed to improve the upper bound very significantly to n times log n, basically, using the extremal theory of matrices. So one of the first results about extremal numbers of matrices is this result of Füredi from 1990, which says that if you have this specific 0, 1 matrix and you want to avoid it, then you can have at most n times log n 1 entries. And he used this result to deduce that the maximum number of unit distance is a convex angle is at most n times log n. And this is actually still the best known bound for this problem for Erdős and Moser up to like the constant factor. The constant factor has since been improved, but it also uses the extremal theory of matrices. So this was one of the first applications and motivations for studying this. And then a more systematic study was started 2 years later by Füredi and Alon. And since then, there have been many applications to various areas of mathematics, like we've already seen this application to combinatorial geometry, but there are lots of other areas like data structures, for example, and there are some very nice surveys about this, but I won't have time to go into too much detail about this. Okay, so what has the research focused on? What are the known results about the extremal numbers of matrices? Much of the research focuses on the case where A is an acyclic matrix, by which I mean that the corresponding bipartite graph is a forest. And the reason that there has been much focus on it is because most of the applications actually use this setting. So for example, if we look back at this result of Füredi, we can see that this matrix A is acyclic. The ones basically don't form a cycle. It actually corresponds to a path with 4 edges. So most of the applications need the case when A is an acyclic matrix. And so there has been a lot of research going into that case. So when A is acyclic, in other words, when the corresponding bipartite is a forest, then the corresponding graph extremal number is of course linear. The extremal numbers of forests are linear in the case of graphs, but the corresponding result is not known. It's still not known in general for matrices. So it's some of the major open problems, perhaps the biggest open problem in the area, to determine if it's true that for every acyclic matrix A, the extremal number is at most n through 1 plus little o1. And even more shocking, I think, is that it's not even known that for acyclic matrices, the extremal number is at most n to the 2 minus epsilon. So there is no known value. It is not known that there is some fixed epsilon greater than 0, not depending on A, such that for every acyclic matrix, the extremal number is at most n to the 2 minus epsilon. And very recently, there has been progress from the low bound side. So previously, it was conjecture that perhaps the extremal number for acyclic matrices is always n times something polylogarithmic. But this was very recently disproved by Petty and Tardos, who showed that you can have the extremal number at least as big as n times 2 to the root log n, basically. So it is faster than n times polylogarithmic, but it's still not known if it's always upper bounded by n to the 1 plus little o1. So given that we don't even understand the case when A is acyclic, it's not very surprising that even less was known about the case where we don't assume that the matrix we're looking at is acyclic. And there's basically only just one general result before I work. It was due to Methuku and Tomon, and to state the result, I will need another definition. So if you have a 0, 1 matrix, I'm going to say that it's column-t-partite if you can cut it between the columns into T submatrices, such that if in each of the T submatrices, every row has at most one entry. So if you look at this matrix A here, then this is column-t-partite, column-2-partite, because you can cut it between the second and the third row, and then, second and the third column, and then you're left with 2 matrices of size 4 by 2, each of which have only one one entry in each row after cutting it between the second and third column. And then the result of Methuku and Tomon from 2022 said that if you have a column-t-partite 0, 1 matrix, then you can give this upper bound on the extremal number. It's basically at most n to the 2 minus 1 over t plus 1 over t squared plus little 1. So this is kind of like an analog of Füredi's theorem, which said that if you have a bipartite graph where every vertex on one side of the bipartition has degree at most t, then the extremal number is n to the 2 minus 1 over t. But there are two major differences here. First of all, in Füredi's theorem, we needed the assumption that the max degree on one side is t. Here, we assume the stronger thing that your matrix is column-t-partite. So the natural equivalent would be to assume that every row has at most t1 entries. But Methuku and Tomon needed the stronger assumption that you can cut it into t submatrices such that every row has one entry, only one entry in each of the submatrices. And the other obvious difference is that Füredi gets the upper bound of 2 minus 1 over t, which is of course tight. But Methuku and Tomon got the exponent 2 minus 1 over t plus 1 over t squared. So in some sense, as t tends to infinity, this is basically tight because the difference 1 over t squared is negligible in some sense when t is very large. But this was definitely not conjectured to be tight in general. And in fact, Methuku and Tomon conjectured that you can remove both of these differences between these theorems. So you can get away with only assuming that every row has only t1 entries, and you can remove the 1 over t squared from the exponent. And our result exactly does that. So we managed to prove this conjecture of Methuku and Tomon and show that if you have at most t1 entries in each row, then the extremal number can be upper bounded by n to the 2 minus 1 over t plus little 1. Okay, so a couple of remarks about this conjecture. So perhaps surprisingly, the little o term in the exponent is needed, at least in the case when t is equal to 1. So this is an old result of Füredi and Alon, which for this specific 0, 1 pattern, you can check that this matrix has only one entry in each row, yet it's known that its extremal function is superlinear. It's on the order of magnitude n times alpha n, where alpha is the inverse Ackermann function. So it's very slowly growing function, alpha n, but it is growing, so the extremal number grows faster than linear. We don't know if it's still necessary, the little o1 term, in the case when t is at least 2, but in one case we know that it's not necessary. When we have the column-t-partite assumption from the theorem of Methuku and Tomon, then we can actually even remove the little o1 term. So in that case, we get just n to the 2 minus 1 over t. And as before, as with the result of Füredi, this theorem is tight, for example, when A is the matrix with only one entries and R rows and T columns. So this corresponds to the case when we had the complete bipartite graph, KRT. That is the bipartite graph corresponding to this matrix. Okay, so I will say very briefly a few words about a proof method and how is it different from many of the other proofs which studied the Turán numbers of 0, 1 matrices. I won't have time to go into too much detail, but I will say just a little bit. So this is our big matrix M, in which we want to find the copy of the small matrix A. So what we do is divide our matrix M into these blocks. We cut it among rows, and then we pass to one of the smaller blocks. And then we cut it again, and then we again pass to smaller blocks. So many proofs which study extremal numbers of matrices do this. Usually what they do is they cut into these blocks and say that if you can't find a copy of your matrix A, then you pass to the densest block in some sense, and then you get some sort of density increment. You forget everything else in the matrix, you only focus on that strip, on that block, and then you repeat. And with these density increments, you get a contradiction. Our proof is going to be quite different because first of all, we will actually not need any density increments. But more importantly, we will not throw away the rest of the matrix after passing to these blocks. So we keep dividing into these blocks and passing to one of the blocks, but we also remember everything else in the matrix because every single step in this process will be used to build a copy of the smaller matrix A. So how do we exactly build a copy of the small matrix A that we want to find in the big matrix? I'm going to focus on things that I'm calling shrinking steps. So let's assume that the small matrix we want to find has only two one entries in each row. In other words, I'm focusing on the case t equals 2 in our result. So because each of the rows of the matrix I'm trying to find has only two one entries, I'm going to focus on pairs of columns. And I'm going to say that a step during this process is shrinking. So when we're going from the blue matrix to the red matrix, this step is shrinking if there's a row which is shared, which is a shared one entry in C1 and C2. So this ith row is one in both C1 and C2, and it's no longer a row in the new matrix. So it is in the blue matrix. It's a row of the blue matrix, but it's not a row of the one matrix of the red matrix. So the number of one entries shared by C1 and C2 decreases during this step. So I'm going to call that step shrinking. So why are shrinking steps useful for us? Basically, if you have lots of shrinking steps for lots of column pairs, then we can easily embed our matrix. For example, let's assume that we want to embed this 0, 1 matrix A shown here, which we can see that has only two one entries in each row. And assume that you have three columns, C1, C2, and C3, that has, let's say all of the steps are shrinking steps for them. So when you're moving from the red matrix to this purple matrix in the last step, it's a shrinking step, so you can find a row in the red thing, which is a 1 in C1 and C3. Similarly, in the blue thing, you can find a row which is a 1 in C2 and C3, and before that in the white, you can find something which is 1 in C1 and C2. So if you look at this, these three shrinking steps together exactly give us a copy of this matrix. So essentially, our proof relies on finding lots of shrinking steps shared by several columns. But I don't really have time to go into too much detail about explaining how we exactly do that. So instead, I'm just going to summarize some of the open problems. So this is the result we proved about matrices which have at most C1 entries. And the most closely related open question that we don't know is whether or not the littler one term is necessary in the case when t is at least 2. As I mentioned, it's necessary in the case when t equals 1, but perhaps that case is somewhat special. There's no example known in the case when t is at least 2. And not that close related to a result, but the most interesting question, I believe, in this area is to determine whether or not the extremal number of acyclic matrices are always n through 1 plus titlo 1, or at least to determine whether it's n to 2 minus epsilon, because I think it's quite surprising that it's still not known. And I think I'm going to stop here, so thank you for your attention.